Thank you. You also and to Giovanni, which is not here, for organizing all of this. So I can share the screen. So I uploaded. Oh, let's do this. Okay. So I uploaded the correction, the notebook with the corrections and all the simulation data on the GitHub repository, which was linked also on the PLUMED website. I will go through, and I also uploaded I also updated the Deep Note project. So if you open it now, you will find the completed tutorials. I will go through the tutorials, the two exercises, and I mean, feel free to interrupt and to ask anything. I mean, since it's a correction, it would be nice also if it would be more interactive, and that's it. So the first exercise was about how to find collective variables from equilibrium fluctuations. So using this DeepLDA method to extract CVs. So here was the summary. So the main idea in general is that we need to the workflow is composed by 3 steps. First, we need to characterize okay, here it is. First, we need to perform some short unbiased simulation in the metastable states. Then we will train a CV based on this data, and finally we can apply a potential to enhance the fluctuation of the of this data-driven CV. And as an example, we are using the As an example, we use as often in this PLUMED Masterclass the RNA and the peptide, but the main idea, which I hope which I hope it passed through this tutorial, was not to use it in a conventional way, like a molecule for which we know already which are the collective variables, the metastable states, and whatever, but try to learn. In a more real life scenario. Okay, so here we have the setup. I can also use this if I need to. So the first step was to create unbiased simulations in the metastable states. So here we had all the setup of both the plumed input file, then also we can run GROMACS from here, and we do this for state A, state B, and then we can load the data. So as we, maybe if I start by executing the setup. Okay, so the first. And so we perform some short unbiased simulation in the 2 states, and then we characterize each configuration with a set of descriptors. What did we use here? We could have used let's say dihedral angles, which of course are more suited to describe the conformational transitions of such a small biomolecule. However, to stress test this method, we started with a less optimal, let's say a suboptimal set of descriptors, which are just plain interatomic distances between heavy atoms. Why are they suboptimal? Well, because if we visualize all of these descriptors, we see that well, I could also avoid running them, but we see that there is not a single descriptor which is able to distinguish between the 2 states. And as you can see here, so these are like histograms for all the 45 heavy atom distances, and there is not a single one which is from which we can say we are in state A or state B according just to this. And if we okay, so from this, what we can do is to train a deeper DACV. Here first, I mean, I put a minimal example like what is actually needed to train such a CV is just to specify a neural network architecture, specify how long we want to train it. For instance, we could specify a fixed number of epochs, or here we use the early stopping method, which means to split the data into training and validation, and stop the training when the validation score does not improve anymore, or it starts to get worse. Okay, this is really like a minimal example. Of course, we can do it in a more. I mean, we can take control of all the different ingredients. Typically, in PyTorch, it's customary to use what are called data loaders, which are let's say some utility functions that automatically take care of taking some batch of data from which we can shuffling them. We can shuffle them. We can move them from one device to the other, so that this is like it's a customary practice which allow us to easily, for instance, train on GPU or CPU, or I mean whatever device is available. So here what we do is to create a data set. We split in train and validation. Here we take 80% of the points to be in the training set and the other in the validation set. And then using this data set, we create this train loader, valid loader, which using this fast Erson data loader. This is actually an improvement, is a modification which is in this MLCVs package for training collective variables, which is actually much faster than the base data loader implemented in Torch, at least for this scenario. Then here I reported a table with all the parameters. What we are doing here is just, just to remember, what we're doing here is training a neural network such that in order to optimize the discrimination of the states. And how do we do this? We do by using the Fisher discriminant ratio as a loss function. So some of the parameters here are related to the neural network architecture. You see the number, the number of layers per node, the kind of activation, rectified linear unit, hyperbolic tangent, and so on and so forth that are implemented. Then we can specify a few hyperparameters regarding to the optimization, such as the learning rate, the regularization, and the number of epochs, and also the parameter for when to stop the training. So as I said at the beginning, since I've seen a few more people join, feel free to interrupt and to ask me if anything is not clear, or you would like to ask some questions or you have comments. Okay, so what we can do, as you can see here, what we do is just we check whether we have, let's say, CUDA installed, and we also have PyTorch CUDA version. And if that, we can use it. Then we define a model. We define a model which is this deeper DACV using what's implemented here is just a fully connected neural network with 2 hidden layers, and then we use we define the optimizer, the regularization, and then finally we fit, passing the train loader, validation loader, and a few more options. I mean, here I wanted to put all the possible details, but as you can see in the couple of cells above, a very minimal example, it is actually way more simple. After having performed the training, what we can do is to check. Well, first of all, we can check at the learning curve, which means how is the loss function, which is here is the eigenvalue of the Fisher discriminant generalized eigenvalue problem, which is a measure of how much the states are separated in the projected CV. And if I can go back above to the to this picture here. So as we see, the structure is the following. In input, we have these input descriptors, like we said, that we are using plane interatomic distances. Then we have a nonlinear transformation of them with the neural network. On the output of the network, we perform LDA, which means we compute the ratio of the so-called between scatter matrix and the within scatter matrix, and we use this information to project the data into a one-dimensional CV. Since there were someone asking in the Slack channel during the last week, the idea is that this framework is completely general and it can work with any number of states, of metastable states, which are here the classes. And of course, the number of the collective variables in output will depend on the number of states. And in general, we will need n-1 CVs to discriminate between the n states. So in this case, which we started only from 2 states, we will have a single CV. If we have 3 states, we have 2 CVs, and so on. If you remember, we started by looking at how are the descriptors, and we see that none of them is able to discriminate between the states. However, after the application of the neural network, and we can look at the output of the neural network, and we see that what the neural network is learning a feature map that maps the input descriptors into some latent space in which the two states are linearly separable. You see that now it will be very easy. I mean, these are the histograms as before. At the beginning, I plotted the histograms of the input features. Here we are plotting the histograms of the outputs of the neural network, and we see that what the network is doing is to learn a transformation such that the space, such that the classes, the metastable states, are linearly separable, and so that the application of LDA results in a maximal effect. Then we can do 2 things here. So first, we can see on the right, we see the histogram of the deep LDA CV. So because the idea is that we have this output space of the neural network, and then we perform LDA. Since we have 2 classes, we said that this will result in just one collective variable, which is the projection of the LDA along the LDA eigenvector. And as you can see, this results in a very sharp, we can say, classifier. So we have a model in such a way, we have a model that tells us whether we have in state A or state B. And this can be also seen by plotting, for instance, the color. I mean, here we plotted the Ramachandran plot as a function of the phi and psi dihedral angles, in which we colored with the deep LDA CV. And we see that this is actually able to discriminate very, very well between 2 states. The blue here is -1 and the red is +1. One interesting thing is someone was asking about the why I choose 5 nodes, five nodes in the last hidden layer, which are the outputs of the network and the inputs of LDA. The reason for choosing 5 is actually very arbitrary, because in general, what we will need to do is I mean, since we are employing a neural network to perform a nonlinear, we are changing the input space, and we are changing always as to maximize the LDA score. So this means that either if we use 10, 5, 3, even 1, in this case, even we could use even just a single output of the network. Of course, 1 is enough in this case because we have only 2 classes. In general, we will need at least n-1 outputs in order to discriminate between the classes, because of course we always need n-1 where CVs to discriminate between them. And here what I did was to make an example, just to repeat the training for different values of the neural network. And as we see that we get we get always very similar results. I mean, the only difference here is that in one case we have, the values of the CV in the 2 states is exchanged, but as you can see here, also the projection is always very sharp. So we are able to it's actually very robust with respect to the number of hidden layers, and even with the number of neural network outputs. Of course, if we try to use, let's say, 1,000, if we have 45 inputs and let's say 1,000 data points, then we won't be able to train a model with billions of parameters, or with, but that's it. Another extra thing I put here, because this was asked in the Slack channel, is how can we compute what's called in machine learning jargon feature relevance, which means can we evaluate a weight of the CV, the weights of the input descriptors in the CVs. This is a field of study in machine learning, and there are a lot of different techniques. Here I put as an example a simple one, which is we can try to estimate a weight of the descriptors by computing the derivatives of the collective variable with respect to all the descriptors and averaging over the training set. So what we define here to be a ranking of the descriptor, the rank, the importance of the descriptor I, and descriptor I will be just here we're missing it will be just the sum over all of the derivatives of the CV with respect to the descriptor I evaluated in a training point J, and then we multiply by the standard deviation, because of course there might be descriptors that are changing, that have a larger range than others. And if you do so, we can obtain a ranking of the feature of the descriptors, and you see we have a few. There are a few which are which are quite dominant, and then they decrease and they go to 0. This is, I mean, this can be understood as percentages, and so they're normalized such that the sum is equal to 1. And as we see here, there are a few. So we might ask, okay, which are these features? Well, for instance, we can plot them, and we see that these are all features. These are all features that are actually, I mean, have a bimodal, at least distribution, in which I mean, if you remember, there were also a lot of other features in which we can go back, in which, okay, see, yes. So there are a lot of features in which we have a partial overlap, and then there are a lot of other features in which the overlap between these two states is really 100%. So it's interesting to see how actually the features that have only the minimal amount of overlap have the greatest weight. On the other, and this is also connected to how to interpret this CV. This is not straightforward because we know. I mean, this example we know that, we know which could be a good collective variable, and this is related to the torsional angles. But we will go back on this later. So I think looking at the derivatives is something which can tell us how much weight each of the descriptors have. Of course, this is one of the many. This is one of the many methods, and another which we can do below after having computed the bias along the DeepLDA-CV is also to look at the correlation between this variable, this DeepLDA-CV, and the descriptors, as well as between DeepLDA and some inputs, some other physical variables. Okay, so the first part was related to the training of the CV. As we see, it's very robust with respect to a lot of parameters, and if you have tried to repeat the training, you will have found very similar results. In the second part, we can bias this CV. So because all of these, it's not just to find classifiers or order parameters to discriminate between steps, but we want to use these collective variables to enhance the sampling. How do we do? As described here, what we do is to export the model. We export the model using Torch script, which is a sort of language implemented within PyTorch, which allows us to serialize the model. This is done under the hood in the export function here, and in which we save the checkpoint, which we could use to load again the model in PyTorch and a Torch script model, which we can use instead, which is a compiled model which can be used to load the collective variable in PLUMED. And as we see here, the input file, PLUMED input file, is very similar to the previous example. What we added is that we first compute the descriptors. As you have seen, the descriptors here are the list of all the 45 distances are in a separate file, PLUMED distances.dat, for convenience. And then we compute the DeepLDA-CV using as we specify which is the file, the compiled PyTorch compiled model, and which are the input descriptors. And then what we do is we use OPES to enhance the sampling. As you can see here, at variance also with metadynamics, we can perform an OPES simulation specifying just as few as 2 parameters. So in this case, the pace and the barrier. And once the simulation is over, we can have a look. So we see, first of all, we can see the time evolution of the collective variable. So these are like 10 nanoseconds. You see, we observe multiple transitions between the states. Of course, these I mean, in this already, I think it wasn't. I mean, it's not something which was granted at the beginning, because as you see, we started from a very suboptimal set of descriptors. Nevertheless, what we see is that this variable, which we knew already was very good at discriminating between the states, it's actually able also to drive somehow the transition between the two. If you, on the right, what we see is I mean, it's just the point explored during the simulation in the Ramachandran plot, and from which we see that we have the state A and state B, and of course we are driving this. So if you are probably you're more familiar with biasing the system with phi and psi. And so the kind, I mean, the region explored will be very different, because that it is. I mean, here we are not biasing phi or psi or all of them together. Rather, we are biasing a nonlinear combination of the distances. So also the region of the phase space which are going to be explored will be very different. As we see, this is able to, from this we can compute the free energy surface and the free energy surface. And as you will see, that since it's like it has been trained like a classifier, what we have here is that the distribution of the width, the standard deviation of the CV within the two minima, especially in this one on the right, is very, very sharp. This is because it was the network was optimized as to push as far as possible the two states away in order to be discriminated the most. What we can do is actually also to compute to recover the free energy as a function of other variables. Here we see along phi and psi, of course, like this region of phi and psi in the Ramachandran plot, so which is like this transition from here to there, and also from state A to B going on the other direction, which has a higher free energy, is not overcome, also due to the OPES barrier. And but of course we are not biasing. So I think we are doing a pretty decent job, even though we are not biasing these variables, and we are just reconstructing their free energy afterwards. Once we have a reasonable sampling, what we can do is actually, as I was saying before, we can try to understand what the neural network has learned. What we can do, for instance, is to compute the correlation between the deep LDA CV and all the input descriptors. This is actually very similar to what we have done before with the derivatives. So with the derivatives of when we compute the derivatives of the deep LDA CV with respect to the input descriptors. As before, I mean, we have a few here. I think the picture is even more complicated. Indeed, we have a lot of descriptors. Well, actually, if we look at the correlation, what we see is that there isn't actually. I mean, we have a lot. I mean, there are a lot of descriptors which have a correlation of 0, and a lot of others which have a correlation of like 0.4. Here we were looking for, let's say, a linear correlation. And indeed, we know that what we're trying to do is learn a nonlinear function of them. So I think in this case, what we can, I mean, understanding a nonlinear correlation between the input and the outputs is actually quite complex, quite complicated. What we can do, an alternative, what we can do is to compute the correlation between, let's say, so what we can do is to compute the correlation between the DPLD-ACV and a set of other physical parameters. So here, what we are doing here is to use a set of very general but also blind descriptors, which are the distances. We are leaving the job of making a good CV out of them to the neural network. But of course, this is the resulting model is quite cryptic. One nice way to interpreting it is rather than just looking at the relationship from the inputs and the outputs, is to compute the correlation of the CV with a set of other physical parameters. Here, it could be, for instance, angles or torsional angles. So in the PLUMED file, we already computed along the trajectory the Ramachandran angles phi and psi, as well as two extra torsional angles, theta and psi. And if we do so, we immediately recognize that there are we have the CV is actually almost a very high correlation with the phi dihedral angles, and a decent anti-correlation also with the psi dihedral angle. So this is a simple example of how we can try to interpret it, what we have found. Of course, however, I will say this is however, this is only half of the story, I would say, because if we look if we plot, here I plotted on the x-axis the DPLD-ACV, while on the y-axis all the different dihedral angles. And we see that, yeah, that's true. There is a correlation between phi and DPLD-A, as well as this anti-correlation between psi and the DPLD-ACV. But still, the relationship is, I mean, it's far from being a linear correlation between them. So what we can learn here is that it's correlated, but it's a non-linear complicated way. Of course, we have done let's say a choice. I mean, the choice we have done when using a neural network to represent, to transform our input descriptors into some collective variables, this is very powerful because it can combine them in a very nonlinear way, can work only when starting from very poor, let's say, very suboptimal descriptors, such as just distances here. On the other hand, interpreting in terms of physical quantities could be more complicated, and of course this is part of the trade-off between accuracy and complexity. But still, I think it's very important to try always to understand, at least I mean, with the simple methods, to try to understand what the CV has learned, because this will allow us to understand when there is a problem, how to solve it. Do you have any questions about this? About this part until here? If not, I will just here. I actually added. I put this exercise in which what we can do is actually to try, as we have seen before, when we were computing the free energy surface as a function of DPLD-ACV, we see that especially this basin here, this state here, is projected into a very narrow minima, and this I mean, this might lead to some artifacts in the sampling, because we will need to use a very I mean, luckily when we use OPAS, we have also a well-behaved adaptive sigma estimation, but still, I mean, if in the limit of the also I think Michele Invernizzi is here, so if he wants to comment. But of course, having a very small, having a very narrow sigma is it's not something which I mean, it might lead to artifacts in the sampling, let's say, because for instance we will need to use very small bandwidth, and also the forces, the resulting forces will be high. And so how can we regularize it? Well, we could try to change, for instance, by adding in the loss function some terms to prevent this, or what we have found to be quite effective in a number of examples was stretching the CV afterwards. So which means, so we see that the CV, as we see the outputs of the CV are like around -1, -1.1, and 1.1, which means that we could, for instance, transform the resulting CV in such a way that it's not we have a linear transformation in the middle of the range, and it's amplifying on around 1. So this can be done, for instance, in a very simple way by using a transformation x plus x cube. Of course, this could be like you could use a lot of different things in which, for instance, I mean, we see that the higher the power and the more linear it becomes on between -1 and 1, and of course it will the more it will be amplified around 1, which is exactly the range of values that we want to stretch in order to have a larger projection in the minima. And here what we see, for instance, is, oh, sorry, yeah, of course, I didn't load it. So as we see here, I mean, the sampling is actually very similar to the previous one, but what we are actually, I mean, the CV we're actually using in this case is the one on the right, which is like x plus x the cube, and in which is actually the width, the basin is slightly larger. We have seen that in a number of different examples that this might help also the bias to also not to get stuck into the minima. But still, it was just a way of playing around, and also and that's it. If you have, do you have any questions about this notebook and this? Yeah, I see a raise hand. Please go ahead.
Okay, thank you. Can you hear me?
Yeah, very well.
So my question is, let's say I have this deep LDA that's trained to distinguish or classify the two states, but the actual transformation then also features another intermediate, metastable intermediate that I do not know a priori.
Yeah.
With this CV, do I get, let's say, reliable free energy of this minima as well, or do I then have to go back and essentially retrain it to distinguish the free states?
Well, I would say it depends. So if I understand correctly, your question is what happens if I have some intermediate states I didn't know of at the beginning. Yeah, thanks. I would say that I mean, of course, in general, the answer is it depends. So will be, of course, like in, I mean, data-driven method, and especially with neural networks, because they are very powerful. But they in general, they are reliable on the data they have been trained on. So in general, if you have some metastable states, I mean, I think there are essentially three options. The first is that you find some intermediate states and your CV is good enough to discriminate. I mean, to promote the same. For instance, if these intermediate states are actually also from a physical perspective, also in the middle, it could be that you are actually able, nevertheless, to drive. I mean, to drive the system back and forth, also across these intermediate states. It could be that this state is so different from the initial ones, and then you get stuck there. And your representation of this, what can you do? Well, you immediately recognize that you are in a new state. Also on this, since it's typically, since this is trained, let's say, as a classifier, this will immediately recognize that this is something different from the states you have trained on. Then what you can do is to take the data from the state and train a DeepLDA CV with 3 states, and this or whatever. Another opportunity, another possibility is that you can also use the TICA approach, which is the subject of the second, to take this suboptimal sampling and make even better CVs out of this. So I will say, I mean, I don't expect this approach to work well in any circumstance. This is like, okay, if I don't know from where to start, what can I do? Well, if I know that I want to go from the liquid to the solid, from a bound to unbound state, from folded to unfolded, I can just try to design a CV based on this information. Will be perfect if then I have also to go through some intermediate state. Well, probably no, but then I know how I can refine it.
Okay, thank you. It's very useful.
Okay, if there aren't any more questions, we can go to the. Sorry, I just need to move. The second tutorial, which was which is about instead TICA. So in the previous example, we were starting from just unbiased simulation in the metastable states, and now we want to go and say, okay, this as I just said, this is like the first step. So we don't know how to start. We have no idea of the kind of CV could be needed to go from one state to the other. Of course, this is not true for RNA peptide, but still, I think this can be useful. Okay. Let's say let's put ourselves in the situation that also Pavel was asking about. So that let's say we used such a CV, we enhanced the sampling, we found maybe we see some transitions, but it's not as good as we were hoping for. So we are not able to accurately reconstruct the free energy. What we can do? Well, what we can do is, and this is what it's illustrated here in this second tutorial, is we can analyze an enhanced sampling simulation, and we can extract what are the slow modes of this bias simulation using this using this variational approach to conformation dynamics, and in particular here we are using this deep TICA approach. In which we extract using a neural network what are the slowly decorrelating modes of the system. So as you will probably have seen, also not only, I mean, the architecture is very, very similar. Of course, it's changing the data. Before we had just unbiased simulation. Now we need to have some reactive, some enhanced sampling simulation. And the way we are optimizing it is not anymore to distinguish between states, rather to identify the slowest mode, the slowly decorrelating modes of the system. And I mean, here there was the introduction. The first here I put two examples, which are actually, I mean, which are a way of describing, which are two possible scenarios. So in the first, we assume we started from a very poor collective variable. And as before, we use this, we use alanine dipeptide. But instead of biasing instead of biasing the right angle phi, we guessed the wrong angle one, which is the psi angle. We thought, okay, looking at this, maybe is the psi angle what we need to enhance. And this, you can replace it to any kind of system and any guess of collective variable that can come to your mind. So we said, let's see what happens if we bias psi. Well, this results in a quite bad sampling. So here we see the time is like 2 microseconds, which for alanine dipeptide is quite a long time. And we see we observe just a few transitions between the states. And also, if you have attended also the first lecture, the first session of the masterclass, you see that this is actually a bad CV. There is a lot of hysteresis and a lot of different stuff. But on the other end, a very nice property of using OPES here is that the bias nevertheless very quickly converges to a quasi-static regime. And so what we are actually, the transitions that we are observing here is actually in a not very far from equilibrium scenario. So here we could reweight this data using a standard umbrella-like reweighting formula. And this is a key point because, of course, extracting data from very out of equilibrium scenario will be much more difficult. While here, when using OPES, maybe we just observe a few transitions in this is really a huge amount of time, but we will see that we are able to extract some useful information out of it. So we first, so let me execute, sorry, so that if I need to plot something. Okay, so here what we do is we plot, we load the data. Here there was, there is this important point, which since we are analyzing a bias simulation, we need to take into account for the effect of the bias potential. And what we need to do is to compute the time correlation functions which are needed for the deep TICA machinery to rescale them based on the value of the bias potential. So what we are assuming here is that the action of the bias potential is accelerating the time, the simulation time. And it's accelerating it by a factor e to the beta v. This is actually very similar to what is assumed when one wants to extract kinetic rates, for instance, from bias simulation. And with this, so first we rescale the time due to the presence of the bias potential, and then we create our data set. In the first example, the dataset was made up by configurations and their labels. Here instead, we have pairs of time-lagged configurations. So configurations at time t and time t plus tau. So configurations which are distant an amount of lag time in the trajectory. And this function here implement this, especially this is important. This is quite tricky when we have in this case we have we don't have an evenly spaced time series like in standard like in the usual case. Rather, we have an exponentially uneven time series. And so the computation of the time lag, the search for the time lag pairs is a bit more. it's numerically way more tricky. Nevertheless, once we have performed such search and we have our data set, what we can do is to train the CV as before. And here we see the parameters are very, very similar to the previous one, because actually what changes is just the way we are using to optimize the network. As before, we can make a comment on the number of outputs of the network, while in the LDA case, we needed at least n-1 outputs, where n is number of states. Of course, here it will depend the number of outputs. They will need to be at least equal to the number of slow modes we want to extract. Here, for instance, I put 2. Then we perform the training. We can see training validation score across the trajectory. We can also look at how as before, also the loss function here is directly connected to the eigenvalues, which tell us how are the resulting variable autocorrelated. Because what we want to do here is to find the maximally autocorrelated functions in the from the bias trajectory. And as before, we can have a look also, for instance, the Ramachandran plot. So here the color is again the diptycha CV. This already is telling us that also this CV is actually acting as a sort of classifier, because we see that it has one value and a quite constant one in one basin, and another value of opposite sign also in the other one. And we will go back on this in a while in the case of multiple CVs. So here I put a few questions and a few, two things to try out. One could repeat the training by changing the loss type. Loss type here means you could optimize the sum of the square of the eigenvectors, of the eigenvalues, just a single one, or just the sum of the eigenvalues. And also you can choose to optimize a different number of eigenvalues. For instance, here we see what happens if we optimize two eigenvalues by just using as a loss function the sum, the sum of them. And here I think this is first of all, here I plotted the scatter plot of the TK1 and TK2. And what we see here is, well, we understand already that deep TK1 CV describe the transition between two states, from which we have just a few transitions between them. While deep TK2 is not so clear what is describing. Another, here what I'm doing is just the same thing. So this is time evolution of deep TK1 and deep TK2 across the trajectory. We see that the deep TK1 is describing actually a rare transition between the states, while the deep TK2 in this case seems just to describe, it just assumes two different values, in the two states, but it doesn't seem like it's describing a transition between at least a slow transition, a rate transition between two states. And also, if we look here if we plot as before the points in the Ramachandran plot according to the deep TK CVs, while we have a very strong signal in the first, in the case of the dominant CV, the deep TK1, in the case of deep TK2, it's not. It's not very clear. Do you have any idea why? Probably this was also some question here. Yeah, based on the free energy profile around the peptide, what will you expect to be the second slowest mode? And do we expect to being able to recover from this simulation or not? Do you have any guess on this? Don't. I think this will be actually much more clear at the end when we also compare with, with the deep TKCVs extracted from different simulation. But we need to remember also that these what we are extracting here are the slow modes of the bias simulation. And our initial enhanced sampling simulation in this case was performed biasing the psi angle, which means that what we try to do is to make to enhance the fluctuation of psi, and so to make transition along them faster, and that's it. I think I will go back on this a little later. As before, what we can do, what we will try to do is before to compute the derivatives of the CV with respect to the descriptors. It's actually interesting to note that a few, if we compare, okay, so here for instance, the distance between 611, 511, 6, 7, 16, and actually this is quite similar, 511, 611, 5 rather than 6, 16. But so the important descriptors are actually, in this case, are similar with deep LDA and deep TCAM. Yet, this is just the histogram. Yet we will see that also we will see, if I think in a while, that they are. This is just, as I was saying, this is just half of the story. Also, because when we compute the derivatives, okay, what we do is to compute an average over all the training set, and so what we are losing a lot of information in doing this. I see a raised hand, please go ahead. Was a mistake maybe? Okay, and what we can actually also do is to another point which I think was also asked during the first lecture was how do we choose the lag time? Well, here while we don't have a very physical interpretation about the choice of the lag time, we have a very simple criterion on how to optimize, how to choose it. We need the lag time to be, we need to choose a lag time such that the eigenvalues that we want to recover from the simulation are not decayed to zero, so we don't want to use too large eigenvalues, too large lag times, and we want to avoid degeneracy at the which could occur in the limit of too small lag times. Here I repeated the training by changing the value of the lag time in a log scale, so from 0.1 up to 1000. And what we can actually, what I plotted here is the value of the eigenvalues in log scale in this range. So we see that if we use a too small lag time, what we will have is that the two eigenvalues, the blue is the dominant one and the orange is the second one, is actually, they're almost degenerate, while in the limit of too large lag times. I mean, here you see that the blue one is decaying very slowly, while the orange one, the second, which is the second eigenvalue, is decaying much faster. And of course, the signal to noise ratio will be very small, and so it will be very difficult to recover, let's say, also the second eigenvector and corresponding eigenvalue using a lag time of 1000. So here, I think a reasonable range of values from which we can choose is something like between 1 and 100, and you see it's quite and if you try to repeat the training on this, if we are interested, of course, in recovering all the two eigenvalues here, if we are interested only on the first, then we see that I mean, before it decaying, before the leading eigenvalue decays, it will take a lot of time. And as before, so we said, okay, we understand that the deep TK1 is associated to a rate transition, as we see here. So we can decide to bias it in order to accelerate this event. And if we do so, what we will see is that we are actually able to promote the sampling between one state to the other. And this is actually quite, I think, I mean, okay, it's alanine the peptide, of course, but it's still quite remarkable that we started from a simulation in which we had like 3-4 transitions in several microseconds, and now we have we can converge a free energies in a matter of a few nanoseconds. So this is, I think, it's very important because it tells us that a huge speed up. So here we have a speed up of like 3 orders of magnitudes can be achieved if we have a way to identify good CVs. And the very nice thing is that here with this method we can identify CVs from bias simulation performed using a very, let's say, also a very suboptimal CV, a very poor CV in the first place. As you see here, when we now compute the free energy as a function of deep TK CV, we see that, I mean, it's very well converged in an amount of time which is like a few nanoseconds out of the initial 2 microseconds, and also here, I mean, what I did also here was to compute the correlation between the deep TK CV and a set of dihedral angles. And as we see, the picture is actually quite similar to the deep LDA, because this is a very simple case, but still it's remarkable. It's remarkable that they are actually closer, that also a thing like deep LDA is not so, it provides a CV which is actually also coherent with what we found here when we extract the slow modes. If we look here, this is as before. This is just the relationship between the deep deep TK CV on the x-axis and the phi and all the other torsional angles, and it's really important. As before, I mean, yeah, we see that it's definitely correlated or anti-correlated here, but still it's I mean, it's different. It will be very different than from biasing just phi. The fact that, as before, we are able to take as inputs a set of descriptors of poor descriptors like the distances. Also, in this case, here we are optimizing them in with different criterion, but still we see that we are able to also to understand by looking at the correlation with known physical variables what has the neural network learned. Here there was I mean another small exercise, but I think for the sake of time to just go to the end, to the second example, which was the how to extract. So in the first example, we extracted a CV from a collective variable driven enhanced sampling simulation. However, it could be, and okay, we use Psi, we could have used deep LDA, but of course, I mean, in this case also deep LDA was already very, very good. Here I wanted to report a different scenario, which is instead of starting from CV-based simulation, we can also start from collective variable free simulation, such as a multi-thermal simulation. If you attended also the previous masterclass, this is what Michele has presented. So multi-canonical means, multi-thermal simulation means to sample all the configurations relevant for a set of different thermodynamic conditions, particularly different temperatures. And so this means to use the temperature as a way to drive the transition between the states. And as we see here, this is actually, I mean, it's working. I mean, this simulation is 50 nanoseconds. So it's, using a multi-canonical simulation is much better than using Psi. Still, it's I mean, it's still the free energy will not be will not be perfect, especially because we are not sampling. I mean, we see here that the intermediate regions are quite poorly sampled. As before, what we can do is to take this data and we compute the weights. Here the weights will be the weights needed to reweight a multi-canonical simulation, as described in the OPES paper, also reported here. And as before, we created the time lag data set. We fit, and here we fit directly two eigenvalues, which we can try to understand. And it's and here we see immediately that there is a strong signal also on the second eigenvector. So you see here we can immediately understand that while the deep Theta1 is related to the transition from one state to this other one, the deep Theta2 is describing the transition from these two substates that compose state A in case of RNA peptide. And this can be seen. This can be seen also here plotted as before, the scatter plot of these two CVs and also their time evolution. Here the color is always deep Theta1, so to discriminate. And here we see that deep Theta2 in this case is doing something different because it's actually the question is, let's say we are not talking about RNA peptide, but rather your system of you want to study and you want to understand. So the first thing you would like to understand is whether these CVs are associated to a slow or to a fast mode. And to do so, well, for instance, we could plot the time evolution, and we see as before that the deep Theta1 describes the transition, I mean, a quite rare transition between two states. In the case of deep Theta2, we see that actually when we are in this basin here, so if we look, when we are in this basin, deep Theta2 is actually quite fixed, while when we are in the other, okay, so in this, well, when we are in this other state, we see, it seems like there is, of course, much faster transition, but there is a transition between these two states, between other two states. And one way of doing this is actually to compute the free energy as a function of the Theta CVs. And here we see, okay, the intermediate region is, I mean, there's a lot of uncertainty. Why? Well, because we have no points there. Because since the transition was driven by the energy, by the potential energy as a mean of performing a multi-canonical simulation, we were not actually sampling a lot of points in the intermediate configurations. But still, we see that roughly we will have these two states describe a transition with a barrier of between, I don't know, 30 and 50, we could say. While in the case of the diptycha 2CV, we see that we see two different metastable states, two different basins, but their free energy barrier is much smaller. It's in the order of a few kBt. And well, of course, the right way to do is, I mean, if we look at this plot here, so the right way to do is, of course, if we want to compute the free energy surface along this this variable, we can just project on the x-axis. If we want to do it on the y-axis, what we would like to do is actually compute the free energy profile of the diptycha 2CV only in this basin. Because here we see that instead it's not, I mean, if we don't do this, then all of the data from this other state will be projected on this other, on the projection on the y-axis. And so what we can do is just to apply, I mean, here we can apply a mask and compute the CV, the diptycha 2 CV only when diptycha 1 is greater than 0. And this results in a much better free energy. Also, the barrier, you see, it's slightly higher than before, because before we were projecting actually the stable state from here on top of the free energy barrier along this second direction. And that's it. But I mean, I wanted to do this because, as you see, even if we don't know anything about this system, and we're just analyzing a multi-canonical we did in the paper about the diptycha. We applied this also to the folding of a small protein. So this is something which I think could be really used in a real life scenario. And even if we don't know anything, we can for sure understand that this is this diptycha 1 CV describes the transition between a rare transition between two states, while this other we understood that it's already quite simple. And also the free energy uncertainty here, you see, it's very small because it have been already quite well sampled. So so what we will need to do is to bias only the first CV. And as before, what we can do is to check how are the results changing when changing the lag time. And as we see here, the range of values is different because of course the initial simulation was different, the bias and also the length. The original simulation here was 50 nanoseconds, while in the first case was 2 microseconds. But still, as before, we see that if we want to, let's say, if we want using a lag time between 0.1 and 1 will be quite good values if we want to recover both the two leading CVs. Here I plot, I mean, these are the results of the training for the different values of the lag time from 0.01, 0.1, 1, and 10. And we see that the first CV is always very, I mean, we obtain very similar results for the slowest CV, diptycha 1, while in the range of values in which we don't have degeneracy, nor the second eigenvalue SDK to 0, we see that we obtain very similar results. These results are actually similar also to the other case, but here are much more robust. And so this is like really the criterion to choose the lag time is just simple as this. And so we said we understood that we want to bias the diptycha 1 CV. And as we see, so this is actually we were starting from a multi-canonical simulation with just a few transitions in 50 nanoseconds. When we analyze it and we extract the slowly decorrelating mode of this simulation, what we obtain is is a very diffusive simulation. We see we are going many times back and forth between states, and this allowed to converge the free energy really in a matter of probably as little as 1 nanosecond. So also in this example, this tutorial tells us that we can analyze also collective variable free. This could be applied also to replica exchange or parallel tampering or other kind of bias simulation, as long as we have the ability of reweighting them, so to assign a weight due to the non-sampling that has been applied. And this allows us to greatly improve the sampling and to converge the free energy estimates. And here, as before, we can compute the correlation. We see it's always very similar, of course, because it's because the CV is as in the previous example, the CV is very correlated with both phi but also psi. Okay, before I end, I just wanted to tell you this, which is so here we see that when extracting the CV, when extracting the diptycha CVs from a multi-canonical simulation, which means a simulation performed biasing the potential energy, we are actually biasing, let's say, in a more uniform way. So we are biasing all the degrees of freedom simultaneously somehow, we might say. And these allow actually to recover what are actually also the slow mode of this of this system. So we see that the first TICA CV is associated to the transition from the state A, state B, while the second CV is associated to the transition between these two substates, which, as we've seen, have a free energy barrier which is much smaller between them. In the first simulation, instead, in which we were starting from a simulation biasing the dihedral angle psi, we see that this signal is not as strong. I mean, we see there is something, but still it's a much weaker signal. Why is this? Because in the original simulation, we already made the transition between these two states not to be slow anymore. So even because here we were biasing along the psi angle, which means the y-axis here, and so we already made this degree of freedom fast enough, and so of course the signal is much weaker, while the signal associated with the slowest mode between these two states is still very marked. Of course, so this tells us that what these CVs are telling us, what these CVs are giving us are the slow modes, the slowly decorrelating modes of a bias simulation. So this allow us to systematically improve on the CVs we were using in the first place, or the simulation we were using in the first place. And but of course, the fact that we will have different results based on the kind of the simulation we start from, because of course we are always trying to understand what are the kinetic bottlenecks that are hampering that specific bias simulation from convergence. And with this, I think I finished. This is also quite late, but I would like to. I would be glad to take any questions or comment if you have. Go ahead, Pavel.
Okay, thank you for the very nice lessons. I really appreciate it. I have maybe a bit of a general question, and that is the relationship between the number of input descriptors and then the performance of both the training and then the biasing at the end. If you can comment on that.
You mean from a computational perspective,
Yes. Yeah.
well, that's for sure. That's a good question. I mean, for instance, of course, I mean, like in the plot, it's here. We applied this also to a small protein, which of course, I mean, although for being a protein is very small, it's still quite way. I mean, it's still way larger than unlike peptide. Of course, I mean, if we use, if you do a naive choice, like using all the distances already here, all the distances which are also marked here will be something like 5,000. And the nice thing is that we can train a CV with 5,000 inputs, especially if we have a GPU. This is going to take, I mean, maybe we won't take 1 second, but maybe it'll take 5 minutes. So that's something perfectly doable. Of course, what we don't want to do is, I mean, if we were to apply a bias as a fun, because so the neural network performs a nonlinear, we could say a nonlinear dimensionality reduction between our input space to our CVs, which will be 1, 2. But of course, then if we want to apply an enhanced sampling bias, what we have to do is to compute the derivatives, the partial derivatives of the CV with respect to all the descriptors. So this will mean if we have 5,000 input descriptors to compute at each time step, 5,000 derivatives. And this is, I mean, this is expensive. Yet, for instance, I mean, so in general, what I would suggest is to try to select a subset, I mean, of these descriptors. The nice thing is that this can be done if you check out also the reference paper here. This can be done in a very blind and data-driven way. In the case of quinolin, of the small protein here, what we did was first to train a CV on using as descriptors all the like 5,000 interatomic distances. Also there, of course, it was quite, let's say, we wanted to do it in as blind as possible way. It wasn't the smartest way. Of course, I mean, you adding also the hydral angles, for instance, would be much smarter. But then first, when you have a CV, you can inspect it and ask, what are the descriptors that are counting the most? For instance, one could compute the weights by computing the derivatives. And then what we did was to take, I don't know, the first 200 descriptors according to the ranking of the given by the derivatives, and training a new CV only on using as inputs these 200. And the fact that we are always learning a nonlinear transformation of the inputs into some latent space, with the objective of finding the most the slowest the correlating modes. What we see is that actually the results are very, very similar, either if we use 200 or all 5,000, because we are able to combine them. Of course, we combine them in a different but always nonlinear way. And so, yeah. Then one could also improve the neural network to improve what is called to be sparsity. So to have only to have a function in which the connections only of a subset of a small subset of inputs are different than 0, for instance. This is something which is well known for linear models or for kernel-based methods. For neural networks, putting exactly to 0 all the weights, it's more difficult. But still, the fact that you can add some regularization terms in the loss function to improve sparsity will allow us to more easily select the most important a subset of important descriptors. And then, of course, but as I think, I like to highlight, even computing, I mean, a larger, of course, and if you have tried running the notebooks, you will see that also these CVs, I mean, on Deep Note, they were painfully slow. But that was about, I mean, I'm sorry, but I mean, that was, I mean, still even on a decent workstation, of course, they are much slower than, let's say, just biasing one angle. But as we've seen also here in the results of this, the speed up that we can attain by identifying the right variable is exponentially. So even if we lose, let's say, one order of magnitude, and no, because we need to bias the CV, and also the fact that we need to load the PyTorch compile model into Plume, compute forward pass, backward pass, and so whatever. All of this is actually, I mean, it's of course it's lower than just biasing a single variable, a single angle, or whatever. But on the other side, this allows us to obtain an exponentially speed up. So I think in the end it's worth it, especially if we can do it in a very general, I mean, a blind way, because the time. Typically, the time to find a good CV can also be quite exponentially long. I mean, the human time also, not only the computational time. So, okay. I think I can also actually stop the live stream. But thank again for all this